we start diving into it. So last time around, our big realization was that photons, things that we had for a long time understood to be waves, actually had particle properties. And that was a little bit strange. And that description was essentially like, okay, well then, is it really a wave? Is it really a particle? Is there a definitive way to tell one side or the other? Is it behaving like one? Is it behaving like the other? Is it both at the same time? And the answer was, it kind of just does what it's doing depending on where it's interacting, what it might be doing at that particular moment. If it's just passing through space, minding its own business, it's probably going to behave a lot like a wave. But when it starts to do things like smack into metals for the photoelectric effect, or smack into atoms, like what we saw with the hydrogen emission spectrum, that's when it starts to behave a little bit more like a particle again. And that was strange, and a lot of this essentially was looking at, well, there's some sort of strange dichotomy between these two, that we really don't necessarily have a definitive definition of what the photon is, whether it's a wave or whether it's a particle. But we took some of the ideas surrounding that, and we took some of the ideas of quantization that we had begun to find from many of these different details surrounding light, and Bohr essentially formulated out something like this for hydrogen. And let's focus on kind of one piece at a time here. Basically, we said, okay, well, if there are only allowed to be very particular angular momentums, and if the electron orbits around the atom because of the electric force, then as it turns out, by quantizing that angular momentum, what we end up with are very, very, very specific radii and tangential velocities that the electron is allowed to be in. No other places is it allowed to be in, right? And that radius that we're talking about here, this r sub n, is looking at, okay, if it's the electric force keeping it in a circle, if it's only allowed to have this particular angular momentum, then this radius that's allowed, or the radii that are allowed, are all given by this equation, where r, not r of b, a of b is what we call the Bohr radius, where the Bohr radius really just means radius 1, the very middle one. And then every single orbital beyond that is just essentially some squared value times that initial radius. With each of those, of course, it's moving around in a circle. It has a tangential velocity, and if it is only allowed to be at certain radii, then it's only also allowed to have very certain velocities. So in just the exact same vein, that same description, we get v sub n, each of the velocities of the first, the second, the third, the fourth shell. Now, combining all of this information together, we took, okay, it's some distance away from the proton. There's a potential energy associated with that. It has some velocity as it spins around the orbital. There is some kinetic energy associated with that. If we sum up those two energies together, then we get what's called the Bohr energy, at least for orbital 1. Every other orbital, E sub n, is all based off of that. So the first one that we see is essentially the lowest energy. When they are as close together as possible, the electron and the proton are attracted to each other. They want to be next to each other. So just in the same way that gravitational potential energy was a negative quantity, so too is this electric potential. What we're seeing here is they would very much like to be towards each other, so it takes some energy to pull them apart. The combination of essentially the energy to pull them apart and the brand new kinetic energy that you have spinning around that circle means that you end up with this sort of equation. I'm on the eraser. This sort of equation that tells us where each of those energies is going to be. And again, just like these other two quantities, it's really all based on squares of which orbital you're in. So in this case, what we're taking is the Bohr energy, or the energy associated with orbital 1, and we're finding all of the other energies are just that quantity divided by n squared. And then you get all of these. And this is only showing the first 4, but it technically goes out to infinity, right? There is no limit to where these things actually go out to be. What is the mass? That is the mass of the electron. because that's what's actually doing the orbiting around. So there's a big point that we mentioned in here, though, that essentially this absorption, this emission, these transfers were how the photons were actually entering and leaving from the atoms. If the electrons are only allowed to be in these very specific energies, and absorbing a photon means the electron jumps from one to the other, then the only colors that the atom is actually allowed to interact with are those energies that essentially match up with one of these transitions. If it's not one of these transitions, the photon passes right on by. So, the first thing that we can look at here is essentially, given hydrogen, what is the shortest wavelength emitted by hydrogen? What is the shortest possible wavelength emitted by hydrogen? And I'm just going to kind of walk through this one right here. If we know that every time there's a photon interaction, that means a shift between where the electron is at in its level, then what is the largest possible shift? Because we might remember here, as we're looking at this thing, that the energy of any particular photon goes hc divided by lambda. And hc divided by lambda, in this case, is going to tell us that the shorter the wavelength, the greater the energy. Where's the biggest jump in this picture down here? What do we think? How can I make the jump as large as possible? Yeah, go from n is equal to a billion back down to n is equal to 1. Realistically, even by the time I hit 5, right, we're really close to that maximum energy that we can have before we've quite literally just ripped the electron away. So what we can do here is we can look at this, and we had this simplified version. This is all of the different wavelengths that hydrogen can emit. Right, if you remember when we were talking about this, the Balmer series was when we had that our N final was equal to 2 in that case. But we say we want the biggest possible energy jump between the two of these things. I know I want to end up at level 1, and I'd like to start at infinity is pretty nice, if I can get all the way out there. Or if I can get close, that's fine. What's infinity minus 1? Still infinity. What about infinity squared minus 1? Still infinity squared? I think here, when I'm looking at this, if in initial is supposed to be infinity, and in final is supposed to be 1, infinity squared minus 1 is really not that much different than just infinity, or infinity squared, I should say. So when we're looking at this, then what we've got on top of that fraction, we've got infinity squared times 1, and then we've got infinity squared minus 1. Infinity squared divided by infinity squared, as long as they're the same infinity, that's 1. The shortest wavelength that we can get is 91.18 nanometers. Now, if the infinities weren't the same, and that's a problem for math majors, if the infinities weren't the same, this would be a little bit of a more pesky question to deal with, but we don't have to worry about the differences between integer spaces and real spaces and complex space, none of that stuff. We'll leave that to those math majors. How do we feel, though? Does all of that make sense so far? All right. Where did the wavelength formula come from? That was actually, at the time, that was a guess and check method. But it's from the last set of lectures when we were picking apart the different wavelengths that we were seeing being emitted from hydrogen. We had an equation that described what those wavelengths were before we actually had the full formalized description of why it was this way. But it's just one of those equations that we have kind of pulled out circumstantially. We understood what it was supposed to be. At the end of the day, you can actually solve this out now. If we're taking this energy description and you plug in the different energies, so every single one of these things has to be essentially, this is delta E. the shift between two levels, but if you take the energy difference between any two levels and you tie that into wavelength, then I could take any initial, final, and you can come up with this equation exactly. So, we ran into an interesting situation because this was a leap in our understanding of what was going on with not only the atom, but essentially understanding all of this nonsense about quantization in the first place. Because it told us immediately that not only were the photons quantized, so too were the states of the electrons in the atom. They were only allowed to be in very particular areas. And that kind of worked. See, when we were just looking at the regular full-on emission spectrum as we had seen it before, it matches pretty much perfectly. Nothing gets better than that. It was really, really nice. But for one, when we had multiple electrons in one single atom, which, how many atoms have multiple electrons? All of them, except hydrogen. So anything besides hydrogen had some trouble. And in fact, even the things that behaved a little bit like hydrogen, we could kind of describe those pretty well. Our descriptions so far lined up with those, but anything like neon, that was a mess at that point. Those things that have multiple electrons are suddenly much more difficult to categorize, to quantify what's actually going on with them. This basic description didn't quite work anymore. It gave us insight into the other atoms, but it didn't describe them particularly well. We also ran into this issue that so far I have been showing you guys a bunch of emission spectra like this, but realistically, if we look into it a little bit closer than this, it's a little more complicated. What's going on right here? What I'm basically saying is that this red line that we have been looking at so far is not actually a red line, it is two red lines, side by side. And these other bright lights are also following the exact same thing. Every single one of these lines that we see on the emission spectra are actually a double, a pair of lines grouped right next to each other. Where might that be coming from? What do you guys know about atoms that gets doubled up? Does anybody know? Does anybody remember any of our fun details from that? Not isomers. A little bit back from that. A little bit more basic chemistry. It's the electrons in the orbitals, the different spins as we have seen them. Do you guys remember that in probably a lot of your chemistry courses, when you were first talking about how the electron orbitals actually filled up in the first place? Electrons could either be spin up or spin down. You might also know, now with all of your good physics knowledge that you have picked up through so far this semester, that spinning objects have angular momentum. So the angular momentum that we talked about before, this L, when I'm talking about this, I was specifically talking about the angular momentum of the electron orbiting the proton, that angular momentum. But you might also know that any object that is spinning also has an angular momentum. So this doublet is really being created by the combination of not only the angular momentum. Remember how we got here in the first place. Let me back up for a second. What we had used to predict where these lines should be was this quantization of the angular momentum. We said the angular momentum is only allowed to be n times h bar. And if it's only allowed to be n times h bar, that's how we formalized all of these orbital shells and how we essentially matched all of our data so far in hydrogen. But why is it n times h bar? I'm going to answer that one in a little bit here. But first, I really want to bring up the fact that the angular momentum is very important for where these lines actually show up. So the angular momentum of the electron orbiting around the proton is very, very large. But because the electron is spinning, the electron too has some angular momentum. And that tiny bit of angular momentum is either going to add to or subtract from the angular momentum of the electron about the proton. And that's why we don't end up with one single line. We end up with two lines. A spin up and a spin down. So when you get a little bit more complicated than this, stuff gets messy very quickly. It's part of what this rapidly turns into. But for the most part, what I'm really trying to get at here is that there is more going on beneath the surface. These extra lines, as we call them, so the big bright lines on top are the regular emission spectra, the broad picture of the emissions. But then if you look very closely at any of these lines and realize that it's actually made up of doubles, we call that the fine structure. Because it's really, really tiny, right? For the most part, you don't ever notice it on the full color spectrum. But you do start to notice it if you zoom in really, really far. So what we've got right there is the fine structure. And what this is really beginning to tell us is that there are more things that are quantized than we initially realized that there would be. And while we're talking about some of these quantization things, let me kind of talk about the clapback from photons. For a long time, we understood that photons were definitely waves. We have done plenty of experiments to prove, yes, these are absolutely waves, no doubt about it. And then eventually, after we understood that description for a very long time, somebody came up with a description that basically said, yeah, but they're kind of like particles, aren't they? And that work was pretty undeniable. Right? And of course, that was Einstein. We ended up taking him pretty seriously for that description. But he said, okay, well, this wave thing, it had a speed, it had a frequency, it had a wavelength, all of those good things. But because it's behaving like a particle, it also ends up having a momentum and an energy. And this is a strange thing in its own right, because this is basically telling us here that photons do come with momentum. They don't have mass, but they have momentum, which is a little bit wacky, I realize. It's a very strange thing, but it is true. And a lot of those are details that we're going to unfortunately not look at in super high detail right now. Some of these other things, as we're going to be talking about them, notice this kind of footnote down here at the bottom. Some of these other descriptions are going to be coming at the end of 192 instead, by the time that you're able to talk a little bit more about what's going on with relativity and some of that weird stuff. The rest of Einstein's body of work. But at a certain point, de Broglie, or it's de Broglie or something like that. It's some French pronunciation, so it doesn't make any sense to me because I have been born and raised on English the entire time. But he argued that, hey, wait a minute. What if our understanding of particle versus wave, what if they are not exclusive descriptions? Right? What if particles are essentially exhibiting properties of each one of these two, but are not necessarily definitively in either camp? That means photons behave a lot like waves a lot of the time, but can act like particles the other half of the time, and that's all right, because a photon is not necessarily in either camp, it's just borrowing attributes depending on what it's doing. What if that is true for everything, not just photons? And so he proposed that, okay, well, all particles perhaps act like waves. All of these waves as we have seen them so far are particles. All of these particles as we have seen them so far are waves. And what he came up with was this equation right here. Lambda is equal to h over p, where p is just the momentum of the particle. Now, this description was a little bit strange. Especially because where was the evidence that any sort of other particles we have seen so far behaving like waves? And we really didn't have a ton. One thing that I do want to highlight real fast is this footnote is very, very important. This description of a particle, you can't jump from a momentum description directly into an energy and a wavelength description for particles with mass. We have not talked about all of these equations in high detail. This energy right here, E is equal to mc squared, is not a complete equation. I'm actually very upset with this equation most of the time because it is the pop science equation, but it is incomplete. it is the simplified scenario of that equation being in use. But what we're basically trying to say here is that there is energy associated with having mass. So for some of these particles that have real mass, I don't want you to try and make the jump immediately from E is equal to hc over lambda. Don't do this for particles. This is only true for light, because for particles, we're not considering all of the energy of the particle. Keep that in mind. This de Broglie wavelength, depending on the momentum, is talking specifically about essentially that energy associated with moving. It's not considering the mass energy. And that's a little bit of a spicier thing to fight against. Something that you'll fight against a little bit more next semester, when you actually go through and derive E is equal to mc squared. But anyways, I do want to try this one in a problem real fast. Take this description of a bullet real fast. Take the next just 1 or 2 minutes. Come up with a number for this. What is the de Broglie wavelength of this bullet? Try to calculate this out real fast. Okay, and I want to go through, and I realize I'm not given a lot of time, but it's not a trick question or anything. It's mostly a kind of grind the numbers up real fast kind of equation here. What we're looking at is I want to find what is this wavelength. What is this wavelength? Lambda is equal to h divided by p. The momentum of this bullet right here, as we would see it, and in fact, let me write this down on the bottom. Lambda equal h over p. The momentum of this bullet is just m times v. 10 grams times 500 meters per second. We should end up with 5 kilogram meters per second. Plug that in. Planck's constant divided by 5 lands us at, 1.326 times 10 to the negative 34 meters. So let's back up for a second. 10 to the negative 34 meters. If we go back and look at the size of a hydrogen atom, the smallest it could be is when the electron is in the first orbital. And I'm trying to explain that that size right there is something like 5.29 times 10 to the negative 11th meters. And then we need essentially a mole's worth of orders of magnitude to get down to this size. Are you ever going to notice the de Broglie wavelength of an object in your day-to-day life? No. There's no way. That is such an incredibly imperceptible kind of size that there is no possible way that we would ever notice it. You could work with atoms every day and never have to worry about a wavelength like this. This is simply way too small to ever consider. And this is why this was kind of an unintuitive kind of leap. Like, part of it makes sense that there is a symmetry associated with the universe. All particles behave like waves rather than only certain particles. That, on its face doesn't sound unreasonable. But numbers like this really give a little bit of intuition as to why we would have never seen this before. Why this question would have never come up in the first place. Because these wavelengths, as we see them, are so incredibly tiny that you would never notice. Classical physics does not believe in things like this. These are too small to ever be measured. And I feel almost pretty confident on saying ever be measured. Maybe in the next 1,000 years, but I don't know about that. Maybe I'm being a little bit too cocky on that one. But point that I'm getting at is this is so incredibly small that you're never going to have to see it. You're never going to have to worry about it. But let's say you did want to prove that it's there. Let's say that you did want to prove that the de Broglie wave is not just some sort of fantasy. How could we see it? Well, notice that it only really depends on the momentum. So if we were to focus in on perhaps a particle that is very low in momentum, then perhaps we might have something in our hands that could actually be found here. And the way to do that is perhaps with very small particles, things where this might happen. So let's imagine this for a minute. let's take some sort of crystalline solid, and that really just means any sort of solid material that you've got, some rock. A rock does a great job. Salt does a fantastic job. Any of those would work. Those are essentially crystal in structure. All of the atoms are spaced a same distance apart each time. So let's assume that for this particular rock that we have picked out, we're going to fire some electrons at it, and we are spacing these atoms, or the atoms are naturally spaced, 1 nanometer apart. Then what we've got, effectively, is a grading of sorts. Right? We want to see, essentially, if we can get this wavelength of the electron around this same wavelength of the spacing, then we could calculate out essentially how fast we have to fire the electron to make this happen, so that we could start observing some of these wave properties. It stops behaving like a particle for a little while, and it starts behaving a little bit more like a wave, passing through some sort of grading. So I think I'm just going to run through this one real fast to kind of show you what I mean with this. What I'm really trying to say is that, okay, well, if all of the atoms are spaced 1 nanometer apart, then we are trying to get our de Broglie wavelength around that value. If we can make it around that value, then we can certainly get it to start exhibiting some of those wave-like behaviors. What kinetic energy should we have to make it match this? So here's what I've got to do. Again, let me do this. HC over lambda. This does not work. And somebody reminded me, why did I say this does not work? Particles have mass. Particles that have mass do not work with this equation because our description of that energy is incomplete. We have not gone through all those details. This equation, HC over lambda, works great for photons. It does not work for electrons, does not work for protons, does not work for other particles that have mass. So instead, what we're going to have to do is we're going to have to go through essentially the long way. We're going to have to take this de Broglie wavelength, say h divided by p. Well, P is not the worst in the world. This is just m times v. Where the mass, remember, we're firing off an electron here, so we actually have this quantity. All electrons have the exact same mass, 9.11 times 10 to the negative 31st. Part of one of those intrinsic values of electrons. I know the wavelength. I know lambda, or, well, that lambda is the wavelength. Of course I know the wavelength. I know the mass. I know Planck's constant. I'm looking for kinetic energy. So really I'm looking for a 1/2 mv squared, but I need to find v first because I've already got m. So let me take this equation that I've got up top. Let me solve this thing down for v. v is equal to h divided by m times lambda. When I do something like that, I get a number that I screwed up in my solutions. What I get is a number somewhere around the order of 727,332 meters per second. Plug that into my kinetic energy, and what I find at the end of the day here is something along the lines of 2.410 times 10 to the negative 19th joules. But we would like this to be in electron volts. So the last thing that I'm going to do is I'm going to say, don't forget that there is this conversion between the two. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. When we do that conversion right on over, what we find at the end of the day is something like 1.508 electron volts. Could you use the Planck constant in electron volts? Let me think there for a second. I don't think so. What you run into is that if you use the Planck constant in electron volts, you have to do conversions in other places. Because what we've got going into this with our V, the units of that, so the units of Planck's constant normally are joule seconds. So in this case, we are squaring joules. If we had been using electron volts instead, we would have been squaring electron volts, and then what divides those electron volts back out? Because we certainly don't end up with electron volts squared, we end up with just joules or just electron volts. So you can't just use the Planck's constant in EV right there. You would have to also convert 1/2 of some of your other units. Why I usually recommend just going into standard units when you're doing a lot of the calculation. It just doesn't work super well in this case. Highlight that a little bit more. But a fun part about this number is you probably don't have a good idea of what 1 electron volt is. But basically what this is telling you is that this amount of energy, I know it looks really, really fast. 727,000 meters per second is really, really fast. But you could do this and more with a simple 9-volt battery. In fact, this 1.508 electron volts, if you could take one single electron and you hooked up a standard AA battery, you could generate this kind of speed from that electron. The beautiful thing about the unit like electron volt, it literally just means how much energy does an electron pick up passing through 1 volt. Standard AA battery has 1.5 volts. A 9-volt battery, by name, typically has 9 volts. So getting speeds like this from those electrons is actually not a super difficult thing just because of, I mean, realistically, how light, how small those particles are. Could try to recreate this, although I don't know that you'd have the equipment to make it happen, really. It's the only problem with that. At least to measure some of those details. So, what this is basically leading us to is, okay, well, maybe everything that we have thought to be particles so far actually does have some sort of wave-like background to it as well. Perhaps all of our particles aren't just particles, but they're also sometimes behaving like waves. The question is then, when? If any of you actually went through and watched that Dr. Quantum video, got a question for everyone that did. Did that bother you? Is there anything that sticks out in your mind that you remember particularly well from that that's still kind of bothering you, sitting in the back of your mind? So maybe you did watch it, maybe you didn't. I still do highly recommend it. I love the video myself. I realized afterwards that the one I uploaded is probably not the best quality, but at that point, it was better than the privated video, and the announcement was already out. But point of the matter, more than anything else, is that there's one thing that really stuck out in my mind and really bothered me about that video. It's at the very end. So the electron behaves like a wave sometimes. I was willing to accept that. The electron sometimes acts like a particle. I felt comfortable with that description as well. The thing that I had a problem with is that the video implies towards the very end there that the electron is aware that it's being watched. And that is not something that is being made up in any sense. That is a thing that we have demonstrated. They're not pulling that out of thin air or just writing up a bunch of fiction. We have run sorts of experiments like that to prove that this is the way that electrons do behave. In that same way, they seem to be aware that they're being watched. Watching is something very important, and I'm going to get into that in just a little bit as we continue moving forward. I have an answer to that I had to think about for quite some time to really feel comfortable with my description, but I want to kind of bring that into the forefront of our mind for a minute to kind of sit there while we are discussing some of these other details. Because electrons do indeed act like waves, and one of the biggest places that we'd see them acting like waves is around the atoms. What if we take Bohr's description of the atom, and what if we take this idea that the electron is acting like a wave in this instance? Anytime you have a string, if I pluck a string, if I slap a string, if I do anything to a string, and it's pinned at both ends, so it's not just like free-flowing or anything else like that, what happens? What waves are allowed to exist on the string? We have a special name for it. What are they? Standing waves. Those are the only waves that actually exist on the string. Anything else kind of just falls off immediately. It doesn't continue to be bouncing back around. So if I pluck a string or something else like that, then maybe for a brief instant we have a non-standing wave, but very rapidly it goes back to just a regular standing wave. Everything else falls away from it. Only the standing wave is allowed to exist on the string. What if these electron orbitals are actually just strings? It's a circular string, which is a little bit strange, but think of it maybe a little bit more like a drum. Right, when you beat on a drum or anything else like that. Then we have different standing waves that might be able to exist on this string. That is specifically, if we're looking at all of these different radii for every single energy level, and we say that, okay, well, if it's supposed to be a standing wave, then I always need some integer value of the wavelength to exist on that, then what we end up getting is replace lambda with h over p, because it's an electron. Shift some things around a little bit. What we end up with, our final result, is that the angular momentum of an electron must be equal to n times h bar. That tells us right there, this description, this postulate of Bohr's to quantize the angular momentum of the electron did not come from nothing. It came from the very fact that an electron, if it is going to be acting like a wave, must be a standing wave existing in this orbital. I said this chapters ago at this point, but I'll say it again. Everything is sine waves. Everything is sine waves. They make up everything that we've got. These electron orbitals, these different strings that we've got, everything is an oscillator, everything is a sine wave. All of it comes back down to these very same standing waves that we were talking about. So, this is not a kind of nonsense deal at this point. I want to look at this one, and I think for a lot of these things, just timing-wise, I think I'm just going to run through these. I think that's the best way to go. We've just had enough of these, and let me erase this while I'm looking at it. We've had enough of these, and the amount of time that it's going to take, and I think there's some descriptions here that I think are not landing, not necessarily not landing, it's just some of the problems are a bit complicated. And getting these brand new equations in here and everything else for realistically what is our very last lecture here, I think it's a little bit easier if I just walk through some of these things and show you what I'm thinking about with these for now, because they are not quite intuitive problems anymore. So let's imagine this. A simple model of the atomic nucleus has protons and neutrons confined in a one-dimensional box. What do I mean by a one-dimensional box? How do we actually have a one-dimensional box? Well, there's not sides. That's a little bit more difficult to see. But one of the ways that we often will draw this out is essentially something that looks like, not a razor. Let's draw it like this. Let's draw a box like this. And what I'm going to do is I'm going to say, let's just focus on the x-axis. That's the one that we're going to focus on. What do we see? We can't see your drawing. Yep, I did the exact same thing last time. I do not learn from my mistakes. Thank you. Basically, we're saying that this box has a bottom length L, where L is equal to this 10 femtometer kind of distance. If this is supposed to be a bunch of, or just a string in general, what type of waves can exist on this string? If the proton is indeed acting like a wave, what types of waves must it be? Like everything else, these must be standing waves. So what are the first three energy states? The problem is asking us here, what are the first three energy levels of the proton? Assuming that it's contained within this box, assuming that it's behaving like a wave, what are the first three energies of this wave? So I'm going to draw these things out. I'm going to say, okay, well, my first wave looks like this. It's just my good classic description of a standing wave, complete with my poorly drawn sine wave pictures. The second one, of course, we now see the full wavelength actually included. The third one, now we've got 3 humps. That could be a lot worse. We can kind of get a sense of what those waves are supposed to look like. So let me label these things. Let me call this n is equal to 1, n is equal to 2, n is equal to 3. So now, let's take another look at this. Let me imagine here for a second. Okay. Well, then my wavelengths, they're all based on L, but I can see that wavelength 1 would be, well, I only see half of the wave right now. So this should be 2 times L. Wavelength 2 should be, well, now I've got a full wave on here, so I'm going to say this is just a complete L. And then wavelength 3, at this point, I see 1 full wavelength and then another half. So it only took 2/3 of the length to produce that full wavelength. Now, we say, all right, now I've got my 3 wavelengths, the wavelengths of each energy state for this proton. Now I need to go ahead and take a look at this thing and imagine, okay, how does this tie in with these other things? I'm looking for what? An energy, right? And how is this energy going to play in here? I need to be thinking about its kinetic energy. I need to be finding what is this velocity, what is this mass, so that I can plug those in together to find a kinetic energy of the proton. And what that's going to look like then is we're going to say, okay, well, I can't get energy directly from wavelength. Again, let me draw it out one more time. Let me draw it out one more time, I asked. Please. There we are. Can I just jump directly from energy to wavelength? No, we cannot. That does not work. And the big reason that it does not work is because we are, again, dealing with a proton. And a proton comes with mass. Any proton that comes with mass, that equation does not work for us. So we're not going to use that thing. What we need to instead do is we need to focus in on the de Broglie wavelength description where we said lambda is equal to h divided by p. Because this does work for particles with masses. So let me even get rid of this thing. Get it out of here. Now, let me do the same thing as last time. Replace p with m divided by v. The mass of the proton is a known value. The mass of the proton is just 1.67 times 10 to the negative 27th kilograms. A really tiny value, but not quite as tiny as the electron. So when I do that, let me go ahead and just plug in, or let me rearrange this first. Let me say that v is equal to h over m times lambda. Then when I do that, let me plug in lambda 1, lambda 2, lambda 3. Let me start with lambda 1 at least. So v1 would be equal to then, if we plug in all of those numbers, 1.985 times 10 to the 7th, pretty fast, meters per second. And let me just kind of carry this all the way for a second. Let me deal with 2 and 3 in a second here. Let's go and say, okay, so now we've got a velocity. Now we need to say that the energy is supposed to be a 1/2 mv squared. If energy is supposed to be a 1/2 mv squared, we've got the mass of the proton. We have just solved out for what the velocity should be. So if I plug all of this information in, I land that E1 should be equal to 3.29 times 10 to the negative 13 joules, or 2.054 times 10 to the 6th electron volts, 2.054 mega electron volts. Do we feel all right with that description so far? Kind of an extension of just some of these equations that we have been looking at so far. If it has to be a bunch of standing waves, then there are energies associated with it being such a standing wave. It must have these energies, these velocities. So now I'm going to cheat a little bit to find these other two. Let's make this a little bit easier. What I'm going to do here is I'm going to say, okay, V2, when I solve out for this, let me compare to my original equation. H is the same, M is the same. Lambda, that's halved. V2 is just 2 times V1. Nice and easy. Keep going with it. V3 is just 3 times V1. Nice and easy. Now I'm even going to carry this into what's going on with my energy. Because if I look at my energy, now it's V squared, so if it is 2 times the velocity that we had seen from before, then this is just supposed to be 2 squared times E1. This is supposed to be 3 squared times E1. When I plug in for all of these values as I would be finding these things, what I land on are, for E2, 8.216 mega electron volts and 18.49 mega electron volts. These are the allowed energy states of a proton in the nucleus of an atom. Assuming the proton also is acting a little bit like a wave, which it is. Now, what would happen, for example, if we tried to have a wavelength or a velocity that was not one of these quantities? What would that look like? Does anybody have a guess? Do we have any thoughts on what we would see in a case like that? The answer is really, we simply wouldn't see it. It can't exist. It's not a standing wave. As we have seen on the strings before, when we have these standing waves, they have to be existing in very particular ways. So for a proton to be in an in-between state, it's just an impossibility. It's not something that's allowed to happen. By all of these equations that we've got, the only places we are going to see the proton, the only energy states it's allowed to be in, the only velocities it's allowed to have are these velocities as we have just calculated out right here. Nothing else. And that's what's really strange about this quantization idea, that it's only allowed to be very particular values. It's not just allowed to be anything. When we take a ball and we toss it up into the air, we can pretty definitively at this point calculate exactly what height it's going to reach. We've done that at this point. We know there's even a few different ways to do it. We could do it kinetic energy to potential energy. We could do classic kinematics, but in all of those things, we could change our velocity by any 0.0001, and we would ever so slightly change our height in the exact same way. In quantum mechanics, you can't make those adjustments. There are only very specific values that many of these things are allowed to be in. It's weird. It's wonky. It's why it's all a bunch of nonsense when it boils down to it. Right? When we go back to our actual title slide here, I know I kind of tucked it down here in the very, very bottom of the screen, but I'm talking about a look into the real nonsense. And I know that's nearly impossible to see on this slide. I wanted to show you guys essentially what some of these things, when you're actually working with particles and light and doing experiments on all of those things, what does some of that actually look like? And I imagine actually Casey has probably had his own hand, he's in here, in his own hand in ripping up all of these things that I have lovingly placed down on the table. Is anything left? Do you recognize any of the parts that are still there exactly that haven't been messed with? All of them. All right, we'll take that. It's the very nature of doing research in a university kind of setting. One day, you pass it on to the next generation. It's the circle of life. Okay, so let's kind of back up into our problem as we were talking about it. The last thing that we wanted to do with this is we wanted to say, okay, let's imagine now there's going to be some sort of transition. If we needed to essentially change between these energy states. If the proton was in energy state 2, and it's going to go back down to energy state 1, how would it do that? What would that photon look like? And here's the answer. What we're going to do is we're going to take, it's not jumping from this spot, hang on. It's not jumping from this spot down to 0. What it's doing is it's jumping between level 2 and level 1. So the photon that comes out is going to be the difference between those two. Delta E is going to be the difference between state 2 and state 1. And now we actually can use that wavelength equation. We actually can use the hc divided by lambda because we are specifically talking about a photon leaving with this energy. That energy difference between these two states, if we were to calculate out these numbers, lands somewhere around 9.859. Oh, every single time. I'm going to run into some USB issues in a minute here. 9.859 times 10 to the negative 13th joules, which translates roughly to a wavelength of 2.017 times 10 to the negative 4th nanometers. In nanometers, to try and compare to some of these other values that we have seen before, like our regular wavelength, 600 nanometer, 300 nanometer from the visible spectrum. Very, very, very high energy photon right here. But generally speaking, that's one of the main ways that different particles are able to jump between energy states. Photons carry a lot of that energy for them. So if an electron needs to jump between different states, it's going to either absorb or emit a photon. Similarly, if a proton needs to jump between different states, it's going to absorb or emit a photon. Photons carry a lot of that energy for us. So let's go ahead and dive into some fun descriptions here. I've got just a little bit of context between all of these things. So the top two pictures as we have seen them right here. Albert Einstein and Niels Bohr, I don't want to say that they were necessarily rivals in working with quantum mechanics, but they had very differing views on what it meant. So there's this quote that is often attributed to Einstein that I'm pretty positive is not actually a quote of Einstein's. I'm pretty sure that's a modern myth, but whatever it is. The quote is supposed to go something like this. Insanity is doing the same thing over and over again and expecting different results. The problem with that is that quantum mechanics is doing the same thing over and over again and getting different results every single time. And this is kind of a funny thing to see the comparison here, and I think part of the reason why the quote is attributed with Einstein is because of essentially this difference in opinion of what quantum mechanics meant. See, as we understand it, quantum mechanics at a certain level has true randomness baked into it. When we were first going through a lot of these discoveries, a lot of these equations, talking about them in the first place, there was a question of, is this actually random? Or are we just not sure of the underlying mechanics surrounding it? And at the time, we didn't know. And Einstein was firmly in the camp that everything is predetermined in a sense. There are underlying mechanics describing all of these things in quantum mechanics. Niels Bohr, on the other hand, was focused on no, it's random. Random means random. There is not an underlying mechanic surrounding this. It is truly random. And at this point, we're actually a little bit more sure that the second opinion here is correct. That there is true randomness baked in. There's not some underlying mechanic that we don't understand, but it is just random in nature, surrounding many of these features about the particle waving around and doing things like that. And then, of course, a fan favorite, Richard Feynman, included here as well. Quantum mechanics describes nature as absurd from the point of view of common sense. And yet it fully agrees with experiment. So quantum mechanics, kind of by that way of describing it, is absurd. But it's also one of our most powerful descriptions. It has done a very fantastic job of predicting many, many, many different things, and it is, I mean, there are flaws that we see in theories like this. It doesn't behave well with relativity, and relativity is another strong-standing kind of equation, strong-standing kind of theory. But, we know there are some issues between these two, but we have held on to both of them for so long at this point because both of them have been extremely powerful in describing many of the things going on in the world, or in the universe, really, at a grand level. So, looking at all of these things so far, as we have been talking about these things, these are essentially what we would call old quantum mechanics. Old quantum mechanics were essentially how we were first beginning to understand how things might be quantized. But one of the things that I have kind of glossed over, certainly I have not tried to describe in any sense, is what is the de Broglie wave? When I talk about a string with standing waves on it, we can see the string waving. When we talk about even photons, and I gave this description of the electric and the magnetic field waving, we could still kind of visualize something there as waving. So when we go back to a particle, and we try to describe what is waving, I don't really have it described on here. What is waving is its existence. And I don't mean that as it's waving in and out of existence. I mean where it exists is kind of waving around. It is not in any one particular place when it's behaving like a wave. Just in the exact same way that when I'm looking at a photon, let's go back to this picture that we have seen of the photon so far. I have used this picture a handful of times where we kind of have the wave part but circled in. That oval is essentially the photon, the particle portion of it. But where specifically is the photon? Is it here? Is it here? Is it here? I would argue that there's not really any one particular place that it exists. Instead, what I like to imagine, it's kind of like how we describe many of our regular objects. I don't just think about some sort of object. Let me just pick up. So this is, for example, my pen pad, right? The little thing that holds my pen that I write with all the time. I love this shape because right here in the very middle is kind of a donut shape that we could argue in a sense that if I was to treat it like a point mass, then the point mass would be right in the middle, right in this bullseye spot. But I would also argue that very here on the outside where I'm touching it, it's also here, and it's also here, and it's also on the back, and it's also on the front. And all of these spots that I'm touching are all spots where it exists. Now, the whole concept of a de Broglie wave and how the matter is waving in and out of existence is the idea that this is no longer such a solid object, that it mostly exists within this region, but it's kind of blurred on the edges. Kind of like how a shadow oftentimes doesn't have hard edges. It blurs a little bit. Where that object actually is kind of in a more blurred situation, and we can't necessarily tell by looking at it where it's at in the blur. We just know it is contained somewhere in there. And the thing that tells us about that blur, about where it might be at, is what we call the wave function. Because, of course, it's the wave of the particle. And the wave function on its own is not necessarily telling us exactly where this thing is, but if we square the wave function, we get what we call a probability function, or a probability amplitude, that tells us where the particle might be, if we were to measure it. And this actually has a lot of similarities to what we were talking about in the double slit experiment with light. In the exact same way, instead of existing somewhere, well, photons kind of in the same way are existing. But how we notice them existing is when we see the brightness, when we see that intensity, that energy of the photon. So, let's take a look at it like this. If we had a classical particle, let me just highlight these differences. If we had a classical particle with mass m, with position x, with momentum p, it would look something like this. It's moving along the x-axis, it's got a mass, it's got a momentum, it's doing its own thing, flying along. But if we were to try and describe this in quantum mechanics, one of the ways that we could write this is as if it were a traveling wave. Essentially, the quantum mechanics description of this thing would no longer take it to be a single particle, it would take it to be a wave that is moving along the x-axis. Then if I was to look, and I would say, okay, well then where is it? Based on this picture, where is it? I don't know. There's not an answer, if we're being completely honest. Because if it's supposed to be essentially, if this is supposed to tell us the probability of where it might be, then it could be anywhere along the x-axis, and I don't have any definitive way to know where it actually should be. There's not an answer for that. And that's part of the weird nature surrounding many of these things. While this particle is acting like a wave, I can't actually know where it's at. It could be anywhere. And in a case like this, we know exactly how this thing would be moving because we have a definitive description of how it's traveling. But in doing so, we have lost any sort of knowledge about where it might be. And this is interesting. And this is actually a really important concept. This all has to do with the Heisenberg uncertainty principle. Basically, many of our particles do not end up looking like this necessarily, where they are in infinitely many places. Instead, many of our particles travel like wave packets. A free particle that is moving along some axis looks a lot more like a packet like this. So roughly speaking, what we know, it's kind of like our same description as to talking about where is the object. It's somewhere in here. This is the blur surrounding the actual object. I know it's contained within here, but I'm not exactly sure where it's contained in there. And the more certain I am, the more we can kind of scrunch that down a little bit more. If it's really widespread, then I say, I know it's in here somewhere, but I'm not exactly sure where. It's when we're looking at real classical objects that this kind of shrinks down to such a point that we don't notice it anymore. Those de Broglie wavelengths are so small that we would never consider them anymore. But we run into this issue where things like momentum and position, they're all determined by waves. And waves like what we see right here are also made of more sine waves. My whole point has been it's all sine waves, all the way down. That continues to be true. Sine waves are just made of more sine waves. So to talk about any sort of particle like this in this wave packet, I would essentially have to be looking at the summation of all of these different waves stacked up together to give me some sense of where this object might actually be. But with all that information, essentially, the more I know, the more I am condensing all of this information down, trying to get an exact description of where this thing is, the more information I lose about my momentum. Because it can be anywhere, because it could be moving anywhere, to get a more complete description of where the particle is at, I have to sacrifice information about its momentum. And if we had to sacrifice momentum, or if we had to sacrifice position to get momentum, we run into this issue. We can't know both at the same time, and this is what's known as the uncertainty principle. For a real particle that we're looking at, and I say looking at, really what we have to do is we have to open the box and we have to look, where is this thing actually at? If we go back to our proton in a box description, we have to at a certain point look at the proton and decide where it's at. And we can only get so much information out of that. We can either focus very much into where it's at in its position. And in doing so, to measure its position, we can't possibly measure its velocity, or rather its momentum, at the same time. If we want to know exactly what its momentum is like, then we can't possibly measure the position in the same degree of certainty at the same time. You are always limited in how well you can know either one of these quantities by this relationship right here. Our uncertainty in x times our uncertainty in p must be strictly greater than or equal to h over 2. And that's what we mean with a lot of the uncertainty. It is impossible to know where many of these things are. This all kind of plays into the Schrodinger's cat description, which I am sure you have heard of at this point. The idea behind Schrodinger's cat, and where I think it gets oftentimes misconstrued, let me kind of just run through the description of this to give you a little bit of an idea of what I mean with this. Schrodinger's cat is placed in a box with, you can't see into the box, but I assume it can breathe or it doesn't need to breathe. It is paired with a radioactive sample and a capsule of poison. And the idea is that if that radioactive sample decays, which it does so randomly, if it decays, it releases the poison, it kills the cat. But until you open the box, you don't know whether the cat is alive or dead. But my problem with something like this is there's this idea, when you describe it like that there is a definitive truth. Surely, if somebody could see into the box before we opened the box, we would be able to tell if the cat was alive or dead. But it is essentially only that we can actually know once we open the box. And I don't feel like that description is complete. Actually, I'm pretty certain that it's not. Because that, again, the implication is that there is a definitive truth. And for many of these things, there is not such any definitive truth. What it really means, the particle is not somewhere, but it's got a possibility of being in these other locations. What I mean is that the particle is like a wave. And when we go to open the box, it makes a decision. It reconvenes itself into a particle in one particular spot. It was not behaving like a particle while we were not watching it. It lost that as it was flying around in the box. It is only when we open up the box that it actually re-becomes a particle and behaves like a particle again. And I bring this up because I really wanted to address what's going on with that double slit experiment video. The big key difference between that video and what we were talking about last time is that in that video they were using the electron rather than a photon. And the part that really stood out to me is that the electron is supposed to be self-aware. That it knows when something is measuring it. That it knows when it's being watched. And it starts behaving like a particle again. And that's not inaccurate. But why does it start behaving like a particle? It's not just that it knows that somebody is watching and it makes that decision. It's about how you can watch the electron. We have seen at this point that there are only very particular values that are allowed to exist in quantum mechanics, right? When we're talking about hydrogen, it's not just going to any random color of light. It is going specifically to these very particular colors of light. Interaction is kind of difficult on this level. So the only way that we can actually watch what the electron is doing is to interact with the electron. And by interacting with the electron, we force it to reconvene itself into a particle. And that's why the double slit experiment changes its results depending on whether you're looking or not. Because looking is just the very broad way of saying measuring, interacting with. You can't measure the electron if you are not interacting with it. And by interacting with it, you force it to pick up those particle properties. And that's not unlike what light does, right? Remember that light is oftentimes a wave, but the circumstances that it's behaving like a particle are when it's colliding with other particles. When the photon is absorbed by the metal and spits out electrons in the photoelectric effect, it's behaving like a particle. The process of interaction forces particles to behave like particles. It's only when nothing is interacting with a particle that it kind of relaxes a little bit and becomes a lot more like a wave. So, I want to focus in on these circumstances where we are not interacting with the object, when we're looking at it when it's a little bit more like a wave. Here's what I'm thinking. I would like to kind of work through this one myself real fast, and I'll show you guys what I'm thinking with this, because I think this will make this, going into this next thing, a little bit easier to see. Use the Heisenberg uncertainty principle to calculate the minimum kinetic energy that a particle can have in a box of width L. So what does this mean? We have closed this box. We have put a particle with mass m into a box. We have closed the box. We have not looked at it. We have not interacted with it. That means we have no idea where it is at within the box. Our uncertainty in x is equal to L. So then, okay, we're looking for a minimum kinetic energy based on the Heisenberg uncertainty principle. So let me write that out real fast. Let me go ahead and say delta x times delta P must be strictly greater than or equal to h divided by 2. Kinetic energy scales with velocity, right? I can't ever say that delta P is equal to 0, because if delta P is equal to 0, then delta X must be infinity, or else this relationship does not hold true. So delta P has to be some minimum value, given that we already know what delta X is supposed to be. That minimum value is when we can make this relationship as small as possible. Namely speaking, let me not take greater than or equal to. Let me look at the minimum case. How well can I actually know these two quantities this well? This is the upper limit of certainty that we can have in these numbers. So now, let's go with this. Let's say delta X times delta P is equal to h over 2. What is delta P? It's our uncertainty in the momentum, but momentum is a vector, typically, right? And in being this way, momentum can be pointing to the left. Momentum can also be pointing to the right. If I assume that this thing is centered on 0, if I assume that the entire thing is not moving, that I've just placed it in there somewhere and I've let it go, it started at rest when I closed the box, that means that my change of momentum is going back and forth between my largest positive momentum and my largest negative momentum. Namely, 2 times m times v. Because it could be going left, it could be going right. Either way, not up for me to decide. That's the uncertainty portion. So now I'm going to take delta x times delta p is really equal to L times 2mv must be equal to h over 2. I mean, at a minimum, or it could be larger than that. We're solving out for what v is actually supposed to be here in this case, so what I would find is that v is equal to h divided by 4ml. Now the last thing that I need to do is I need to say, okay, well this is supposed to be kinetic energy, isn't it? 1/2 mv squared. Go ahead and plug in some of these quantities as we've got. I'm going to plug in v squared here, so this is going to turn into a nasty 16 m squared L squared divided, or all of that under h squared. At the end of the day, what I end up with is that my kinetic energy is equal to h squared divided by 32 ml squared. That is the minimum energy that it must have by putting it into the box, by closing up the box, by no longer looking at it, by allowing it to kind of spread out its de Broglie wave throughout the entire box. There is some minimum energy that it has. It's essentially constantly vibrating around a little bit, and that is intrinsic. That is something that we cannot stop. There is never a such thing as zero energy. It's always just a little bit of vibration going on. So, speaking about cats, where is Schrödinger? What is all of that stuff? Here's why we haven't talked about it so far. Let's look at this equation. So piece by piece, we said, okay, the very first thing we see in this equation is I. And that is not just some random variable, that is the imaginary number square root of -1. So if you've ever looked at complex numbers or imaginary numbers and thought, this sounds like a bunch of absolute nonsense that is never going to be realistic or make any sense, I have a rude awakening for you that complex numbers are actually an exceptionally important detail in a lot of different physics, beyond just what we're talking about here. It shows up in all sorts of things like optics as well. It's actually a very important concept. We've got I, we've got the constant h bar. We have the time differential of our wave function. So basically what this left hand is saying is, how does the wave function change in time? Then if we were to integrate that, we could get what the wave function is supposed to be. But this tells us the rate of change of the wave function. On the other side, we've got what we would actually call the Hamiltonian a lot of the time, if you are familiar with that name at all. But really what it is, it's a combination of the different forces acting on it, as well as the different potential energies that would be acting upon our particle. A lot of fun details, all wrapped up in one big equation right here. But all of that stuff kind of mixed in with all of that. But there's why we don't really look at how these wave functions are going to be evolving with time, because it is a much more complex kind of issue to fight with. And I don't mean just complex in the sense that it's using imaginary numbers. I mean, it is a little bit more difficult to deal with. But it is a very, very cool equation, I think. I think it even just kind of looks crazy with all the size included and everything else. It's a neat equation. But anyways, it's not the only way to talk about different sorts of things like this. We can also focus on some other cases that are perhaps a little bit easier to parse. And the easiest case to parse, one of the first things that we like to see in quantum mechanics is what we call the infinite square well, or a box. A one-dimensional box, though. Here's this idea. Particles act a lot like standing waves, because standing waves are essentially the only things that can exist within certain spaces. If something is going to be oscillating within a certain space, if I were to pluck a string, it's not allowed to just vibrate on the sides or anything else. The ends are oftentimes fixed, and if the ends are fixed, then the waves that are actually allowed to exist are only those that are standing waves. So when we look at something like the infinite square well, what we're basically seeing here is we've got some sort of box. We have these infinitely tall cliffs that the particle can certainly never get into, called a classically forbidden region. And so these black dots that I've kind of drawn here, what I'm trying to imply here is that the particle cannot be here. The particle can't be halfway into the cliff. It just doesn't work. It has to be outside of the cliff. So if the condition is that the particle certainly can't be on this side, and the particle certainly can't be on this side, what sort of waves can exist in such a system? And the answer, of course, is more standing waves, the most basic of which being something like this. That right there is the shape of the lowest wave function. It's all of these. The solutions all look like standing waves on a string. So for all of these, what we can do is we can take essentially the difference between the wave function and the probability function is that the probability function is going to be just squaring the wave function. So it's a sine wave squared. So another full sine wave squared. It's another full sine wave squared. And each of these, notice that the probability is exclusively positive, which is probably not a crazy thing, I would think. What is the negative probability of something happening? It doesn't mean anything. So we're exclusively looking at positive probabilities. That's why it's always squared like this. But basically what we know is that if it's contained inside of the box, if we see this thing right there, we know it's inside the box. What's the probability of finding the particle inside the box? Give me a number here. What do we think? Any guesses? 100%, that's what I like to see. Or 1, if we wanted to draw it just out as a number. So that is to say, if there's a little bit of uncertainty, and I mean that kind of in a pun sense, but not entirely, if we don't necessarily know what these values are, but we do know things that they are contained within this region, then what we could say is that if you were to group over all of space, if I look all the way from the left, all the way out to the right, then I know the particle has to exist somewhere. The probability of it existing is 1. When we go through all of those steps and we actually look at what's going to play into each of those, we get some equations for at least the finite square, or the infinite square well. We get 2 equations like this. The wave function, as we would see it, and the energy for each level that the particle could be in. Where again, first, second, third, fourth, which level are we looking at? All of those things slapped together. So I want to take this idea real fast. Let's actually, I think we've got enough time that we can work on this one a little bit. I want you to take a picture like this, based on what you see right here. So I have given you the wave function. Not the probability, but the wave function. I want you to take the next, just say 4 or 5 minutes to try to plot this one out. To imagine, okay, well, we've got the wave function here. What does the probability function look like based on this? Knowing that the particle must exist somewhere on this graph, what is the constant value c? And then finally, what is the probability that you're going to find that particle between -1 and +1? So take the next 4 or 5 minutes, try this one out, see if you can come up with some good things here. And then we'll come back together and see if we're all thinking the same thing. Okay, let's go ahead and talk about what I'm thinking for this one and see if you guys are coming up with kind of matching ideas here. So, and let me even go ahead and let's steal this picture as we've got it right here. And I'm actually going to take this thing and paste it twice in. One time, 2 times. Because I want to have some reference picture all the way back at the beginning here, but I think what I'm going to do is I'm going to try and combine the two of these things together. So looking at just my wave function, that is not my probability function. But instead what I'm going to need to do is I'm going to need to take each quantity as we would see it, and I'm going to essentially stack on top what I think this squared would look like. Here's what I'm thinking. -1/2 c squared is going to become 1/4 c squared. So let's go ahead and replace some of these things. Let me call this like a c squared. Let me call this like a c squared. Then my actual function now is not going to be this. I'll do it in a slightly different, let's do it in green so it really stands out. It's going to go halfway up for that entire stretch. Now, c squared is going to continue to be c squared. Am I on a spot that you can't see again? Yes, I am. Thank you. As soon as I saw the message pop up, I knew. Something like this. I've tried to erase. So what I've done is I've erased down what's going on in the bottom. I've said, okay, well, the 1/2 c squared, 1/2 c squared becomes 1/4 c squared. So it comes halfway up now. My c squared is just 1 times c squared. So this thing should just continue to be c squared. I have changed my units up here at the top just a little bit. Cuts all the way across, and then the exact same thing going on down here. I have a -1/2 c squared is going to end up something like this instead. So let's erase these bits that we don't really care about. We don't need any of this stuff now. We are exclusively looking at the positive axis at this point. Get rid of that stuff as well. Something beautiful just like this. So that's what I would expect to see out of this probability function. Now, what else are we looking for here? In this case, we are looking for the value of the constant c. Okay, well that's a little bit interesting, but that's all right, because we know that it has to be included here somewhere. That means if I were to take all of these different parts and I add them all up together, namely, if I look at this spot right here, for a length of 1 nanometer times, I'm zoomed in a little bit more than I expect to be, 1 nanometer times 1/4 c squared plus my center section, which is just a full 2 times c squared, 2 nanometers times c squared. Got my third section, which is just another 1 nanometer times 1/4 c squared. All of that has to sum together to be equal to 1 because I know the particle has to be somewhere included in all of that. So when I actually start to stack these values together, here's what I'm going to end up with. 0.25 nanometers, 0.25 nanometers on the left, 0.25 nanometers on the right, 2.5 nanometers times c squared is equal to 1. A couple different ways that I could handle it at this point. I could solve out for C in terms of nanometers. That would be, I think, totally fine, actually. Let's just go ahead and do that. I think that's probably the easier way to go about things. So 1 divided by 2.5 is going to end up as 0.4. 0.4, yeah. Take it as 0.4. Considering all of these units to be in something like nanometers, take the square root of 0.4, and actually that number turns out to be something a little bit nasty, like 0.632. Are we feeling all right with that stuff so far, though? Anything crazy going into all of this, or are we feeling like that's reasonable, perhaps? So then the question last is, what is the probability that we are going to be somewhere in this middle section? We said between -1 and 1. There's a few different ways. For one, we could imagine, let's just plug in with our brand new value for C right here. If we plug in with this value, what would we end up finding? Well, that's one way to do it. Or I could look at this and I could say, hey, wasn't this portion 2? Weren't these other portions essentially added up together out of 0.5? What I am seeing right here, if I'm taking this central quantity, is that the probability of being right there in the middle is 2 nanometers divided by, or just not even 2 nanometers, just 2 divided by 2.5. That is the size of my center block as compared to the entire shape, all highlighted in green. There's an 80% probability to be between -1 and +1. And that's one of those things that we can't know until we actually measure it. This is the probability that it's going to be in any one of these particular areas, but until we actually open up the box, interact with the particle, and measure it, we don't know necessarily where it's going to be at. We just know that there's an 80% chance that we're going to find it in this central region. So, I want to just kind of dig through the last of this little bit, and by dig, I mean tunneling. See, talking about these standing wave descriptions, for the most part, they're very, very, very good descriptions. Most things exist as standing waves. But there are some things that might messy that up just a little bit. For example, if we were looking back at our square well, but we made the cliffs not infinitely tall. Really tall, but not infinitely tall. What we would begin to see then is that the probability of the particle, or rather, let me talk about the wave function first. The wave function of the particle doesn't necessarily just end at these edges. What we instead get is this kind of bleeding into the walls. Just a little bit. It shifts all of the energies ever so slightly. And because of that, we have what looks a lot like a standing wave, but it looks a little bit more as if what were to happen if perhaps you're doing jump rope with a friend and you're shaking, you're making these standing waves, and they're not super comfortable in their grip and their arms kind of waving a little bit like this. Then the wave that as it travels into their arm and where that energy goes looks a little bit like what we're seeing here on the outside. Some of the energy, some of the amplitude leaves through the outside. And that means that the total energy, the frequency, all of those things shift ever so slightly, the probability function where it changes. We can see now the particle is a lot more likely to show up right next to the wall than it was before. But there's this possibility that the particle might be found inside of the barrier, and that is not actually one of those likely scenarios that we would necessarily see all of the time, because how does a particle actually show up on the barrier? We don't necessarily have a fantastic way of measuring that. But instead, let's imagine something like this. Let's talk about essentially what is that depth? How far could it go into the barrier? If it would go into the barrier, we get a penetration depth, something like this. If it's going to travel some distance eta out, This value is what we call the penetration depth, and it's calculated essentially by how much energy the particle has versus how much energy it would need to jump over that barrier. Sometimes it can borrow just a little bit of energy and end up on top of the barrier instead. But the more exciting thing about this is not to focus in on what's going on with the penetration depth, it's to actually look at what happens when that wall is not infinitely long. What happens when the energy barrier is just a short little wall, a stack? Then what we end up getting here is that we're combining essentially what we see with the penetration depth, where we have this exponential decay of the probability paired with the fact that at a certain point it is going to exit out. And then from there on out, it's free again. It's back to having no extra potential trying to block it. It's allowed to move like a wave again. So what we've got is we've got a large probability that the particle is going to be found inside of our well, with a small possibility that the particle might escape and travel outwards to tunnel. And I know this sounds a lot like a sci-fi concept, but I would like to explain that it's really not. This is one of those principles that is a very, very real thing. It sounds sci-fi, but it's a very real thing. In fact, many transistors and computer processors at this point are running into issues because of how small they're getting, that these energy barriers are kind of allowing the electrons to jump back and forth between paths that they really shouldn't. And that's a big deal, because if you've got electrons jumping in paths that they shouldn't, then you're getting essentially wrong bits in places that they really shouldn't be wrong. We also run into this if you're ever working with an electron microscope. An electron microscope doesn't use light. It only works on conductive materials, because really what it's doing there is it's setting up a big large plane and it charges it. It puts a whole bunch of electrons on whatever you're trying to look at. And then you take an atom's thick gold needle and you run it over top. And depending on how close that object is, more or less electrons will tunnel up to your gold needle. And using that, by kind of scanning the gold needle around and looking at how many electrons jump up onto the gold needle, you're able to recreate a picture of how close, what does that object actually look like. And you can get a lot more of a precise look at many of these objects than you could with just working with visible light. For whatever reason. There might be a few different reasons that light doesn't work super well. But at the end of the day, you get essentially a probability of tunneling depending on how wide is the barrier, how much energy do we have going into it from before. And the last thing that we can do here is we can actually calculate out what this would be. If we were to take an electron that has 4.8 electron volts of energy, and it sees a 1 nanometer wide potential energy barrier with a height of 5 electron volts, what is the probability that it would go through the barrier? Let me kind of just work through this one real fast. We're going to start towards the very end of this. We're going to say probability is equal to negative 2e to the negative 2w divided by eta. Okay, well, we know the width. The width is given to us as 1 nanometer. Looking towards eta, though, that's the spot where it's a little bit more complicated. We've got h bar divided by the square root of this whole nasty thing, 2m mu naught minus e. And notice what goes on in an equation like this. When we're actually looking at this thing, what we can basically say is, okay, well, it's based on these pieces of information. If E is actually larger than the potential, if our energy is actually floating up somewhere over here, then this ripple effect is going to cause kind of like a wave in the ocean, right? It's going to cause like a weird spike in the wave. It's going to cause a weird shape, but it's able to freely flow directly over top of the barrier. It's only when we're lower than the barrier that we actually have to worry about penetration. So with all of these things, we can say, all right, well, the electron, as we know, is going to have a mass of 9.11 times 10 to the negative 31st kilograms. We know what the energy is in electron volts, and we probably, let me think here, we probably want to convert this into standard units. That is probably the best thing to do at this point. So what I would do is I would convert my potential energies into, or better yet, let me take the difference between the two. Let's take the 0.2 electron volts as the difference between those two. Let's go ahead and convert that back into what we would see for joules, so this would become 3.2 times 10 to the negative 20th joules times the mass, all of that square root under h bar. And what we should find with all of that, where did I put this number? I think I wrote this down in a bad spot. Where did I put this number? Oh no. What did I do with this? Hang on. Sorry. I had my momentum going and now I've ended up stopping myself. Fool that I am. There we are. Okay, sorry. I just had to find where that actually was. When we plug all of those numbers in, what we find for our penetration depth is something along the order of 4.35 times 10 to the negative 10th meters. And that's not to say that we're not going to get some tunneling through. That's just basically saying we lose a large portion of it. Notice that we are only getting essentially 37% by the time we have hit the penetration depth. So to go another one down, we're essentially continuing to decrease how many are going down, but as long as there is some end, there is always some probability that we're going to be tunneling through. But now at this point, we have calculated eta, we have been given the width. When we plug all of these values together, what we end up with is right around a 1% probability of tunneling, and that is more than enough to see plenty of tunneling. This is essentially the chance of tunneling within some sort of given a certain time frame. But that's more than enough. If you have billions of electrons, which is not a small number of electrons, but it's not super large either, you would see plenty of electrons tunneling through any sort of forbidden barrier. How do we feel, team? I know I've run through a lot of the whiteboards today, and I apologize for that. I felt, what was the value for h bar? That is, h bar is h divided by 2 pi. Absolutely. So I apologize. There's a fair bit of information that I did want to get included in this in some way or another to talk about many of these details, to have this romp through a lot of our quantum mechanics stuff. But while we are closing out, this really is our last lecture of covering material. So hopefully I will see plenty of you Wednesday to answer plenty of questions and have chats with you in office hours and all that good stuff as well. But I did want to take a chance to thank you guys for going through the course like this, for getting through it. Congratulations, pat yourself on the back. You have made it this far. That is all of the material that 191 is going to cover, and I thank you for going through it with me.